Hi everybody! In this video, I will go over a multiple choice exam based on Unit 2. Unit 2 encompasses videos 2.1 all the way to 2.13, so do be expecting a lot of material. So let's go over this test together, and hopefully you try this on your own first, and once you're done with it, you can come here and watch the video. But if you just want to watch just for fun, or if you want to watch to see what I do, then feel free, because as long as you learn, that's the point, right? So now let's begin. Number 1. What is the name of H3PO3 aqueous? Now, what type of compound is this? Well, we see H's and we see an aqueous form, so this is a dead giveaway that it is an acid. So we'll name it as if it were an acid, so we have to focus on the anion. So PO3 will be, I think it will be phosphite. The reason why I think it's phosphite is because it's just phosphate, but with one oxygen removed. So going from PO43- to PO33-, so the ite would fit that. So we have to change the phosphite into its acidic form, so we have to name it as phosphorus acid. So notice how I added the OR before the OUS, because for things with P or S, we have to do this for the acids. It's just a special thing. So therefore, our answer will be D, phosphorus acid. Number 2, what is the name of HCl gas? Now this is not an acid since it lacks the aqueous form. Instead, it is a gas form. And if that is so, then it is a covalent compound, and we have to name it like that. So it would not be A or D or B, because for B, the second element ends with an INE instead of an IDE. So our only answer is C. But you might be thinking, shouldn't the answer be hydrogen monochloride? Well, yes, but scientists like to call it hydrogen chloride instead, because it is redundant to include the monochloride, since HCl gas only exists in one form in a 1-to-1 ratio. And I talked about this in the video about naming covalent compounds. So this question could have been solved by crossing out all the wrong answers, or simply just knowing that HCl gas can be called hydrogen chloride or hydrogen monochloride, although you tend to see hydrogen chloride more commonly. Now, let's go on to question 3. Which of the following of Dalton's atomic theory is technically not true? A. An element is composed of atoms. We know that that is true, so we can cross that out. All atoms of an element are identical. Now, this is not true because atoms of an element can have differing number of neutrons, so they are called isotopes, and therefore B is our correct answer. And note that for the other 3, they are just the other points of Dalton's atomic theory that are true. So atoms in an element are different from the atoms of another element. That is true. In a chemical reaction, atoms move from one substance to another. That's true. And compounds are formed when 2 or more elements combine. That is true. So B is our answer. Let's move on to the next question. Will thallium-203 likely be stable? Well, let's look at this. So we know that this is 81 and 203 thallium. So let's see if the neutron to proton ratio is stable. Now, if you remember, elements with an atomic number between 50 and around 80 are stable when their neutron to proton ratio is 1.5 to 1. So let's calculate the neutron to proton ratio for thallium-203. So the number of neutrons is just 203 minus 81, and that will get us 122, and we have to set that in relation to the number of protons. So the number of protons is just 81. Now if you divide 122 divided by 81, you get around 1.5 0.06 to 1. Notice how I'm ignoring sig figs. So it does seem like thallium-203 is relatively stable, since it has a neutron to proton ratio of about 1.5 to 1. Even though it's not exact, it's pretty close, so I would say yes for the first one. And what about tritium with, you know, a mass number of 3 and an atomic number of 1? Now this has 2 neutrons and 1 proton. Now we said that for elements that have an atomic number of less than 20, I think, they will have a 1-to-1 ratio to be stable. And this is 2-to-1 and not 1-to-1, so obviously tritium is not stable. So this will be no, and therefore our answer will be yes and no, C. So all in all, if you have too many neutrons or too few neutrons, then you will not be stable, and you have to have a certain number of neutrons depending on the number of protons you have. So usually, the more protons you have, the more of a neutron to proton ratio you need to have in order to be stable. So that's why for things with an atomic number of 1, you need a 1-to-1 ratio, while for things with an atomic number of 80, you need something like a 1.5 to 1 ratio, which is a lot higher. So now let's move on to our next question. Which of the following is a radioactive element? So in order to solve this problem, we have to have a periodic table out. So we have to find which ones are radioactive elements. In other words, which ones are unstable. And I talked about these before. These are also known as the synthetic elements, since the synthetic elements cannot exist in nature since they are not stable and thus radioactive. So let's find the unstable elements, or the radioactive elements. So in this case, sodium is not radioactive because it's less than 94. So let's put the marker here. Chromium is less than 94. Nobelium. Now nobelium is actually higher than 94. So let me try to locate it. Nobelium. Wow. Let me try to find it. NB. Oh, found it. It's right there. It has an atomic number of 102. This is far higher than 94, which is the highest you can go before you become synthetic and before you become impossible to exist in nature, and that's why you're called a synthetic element. So thus, nobelium is our answer, and mercury is 80, which is less than 94, so that's out. And let's now do number 6. So I kind of forgot, but I think I'm covering up number 6 with this chart, so let me just delete this chart. So I'm just going to delete the chart and clear the ink, and let me recircle the answers. And now let's do number 6. What are the sums of the coefficient of the balanced reaction? So we have to balance this first. So how do we balance this? Well, let's find the number of nitrogens, hydrogens, and oxygens. So on the left-hand side, we have 4 nitrogens, we have 4 hydrogens, and 4 oxygens. On the right-hand side, we have 2 nitrogens, 2 hydrogens, and 1 oxygen. So to first balance this, I think I would naturally add a 4 here. So if I add a 4 there, then this becomes 4, and this becomes 8. So now we balance the oxygens, and now our hydrogens are unbalanced. So let's balance the hydrogens out. So if we want 4 to become 8, we put a 2 here, and now we just cross this out, and instead of 4, we actually have 8 hydrogens now, and instead of 4 nitrogens, we actually have 6 nitrogens. And notice how our nitrogens are now unbalanced. So let's balance our nitrogens. So if there's 6 here and 2 here, we want to make the 2 is 6. So I think I would put 3 here because 3 times 2 is 6. And note that how the elements on the left and right are balanced. So 6, 6, 8, 8, and 4, 4. And although that looks kind of confusing, it works. So we got the atoms on both sides to match. So now let's add up the coefficients. So when you add them up, it's going to be 2 plus 1. Remember, there's an invisible 1 there that's not written, but it's still there. And there's 3 and 4. So what's 2 plus 1? 2 plus 1 is 3. 3 plus 3 is 6. And 6 plus 4 is 10. So our answer is 10 here. Let's move on to the next question. Which of the following statements about the above reaction is incorrect? So our reaction is here. 1 mole of elemental phosphorus, P4, reacts with 5 moles of oxygen gas to produce 1 mole of phosphorus pentoxide. Now you might notice how phosphorus pentoxide is PO5, but the thing is that scientists like to call P4O10 phosphorus pentoxide for some reason, because I guess if you kind of just multiply this by 2, you get P2O10, but instead of the 2, you have a 4. So don't worry about that. It's just something that scientists like to do, and that's not the question anyways. So let's look at the question. 1 mole of P4 and 5 moles of O2 produces 1 mole of P4O10. So this is absolutely right, because remember, reactions can be read in terms of moles or molecules. So A is right, so we can cross that out. 1 molecule of P4 and 5 molecules of O2 react to form 1 molecule of P4O10. So this is right as well, because we can read reactions in moles or molecules. The reaction goes to completion. Well, in a video about electrolytes, I talked about how the single arrow tells us that the reaction goes 100% through, or really close to 100%. So that's right as well. Now let's look at D. The reaction P4O10 becomes P4 plus 5O2 goes to completion. Now, if this forward reaction goes to completion, how can the backward reaction go to completion? Because if the reaction likes to go this way, then it would not like to go backwards or this way, which is what this reaction is showing. This reaction is showing the reaction going backwards. And since the reaction only likes going forwards, as indicated by the single arrow, then it will not go backwards, and thus this backward reaction will not go to completion. So D is the correct answer here. Now let's move on to number 8. This one seems to involve empirical and molecular formulas. So let's make a table and convert our percentages to grams. So we're going to assume 100 grams, and now let's try to find the empirical formula. So 57.14 grams of carbon, and for hydrogen 6.16 grams, for nitrogen 9.52 grams, and for oxygen 27.18 grams. Now I'm not going to show you, but I'm going to convert all of this into moles. So here are the moles of each element, and now I'm going to divide by the smallest of them. So the smallest of them is actually, I think it's 0.6795. So let me get doing that, and I'll show you the results. So these are the results, and notice how I rounded them. So this answer was actually 8.9757, but since 8.97 is so close to 9, I just rounded to 9. But on your calculator, if you get something like 8.9, that's not close enough to 9. It has to be like 8.99 or 8.97, so you have to be really close, like 0.03 or 0.02 off in order to round, and that's why I did that. So this is your ratios, and notice how we can't have decimal ratios, so we have to make them all whole numbers. So let's scale it up. So 7 becomes 14, 9 becomes 18, 1 becomes 2, and 2.5 becomes 5. So I scaled everything up by 2 for each of them, and notice how the 2.5 becomes a whole number. So C14, H18, and 2O5 is our empirical formula. So let me write that. C14, H18, and 2O5. Now let's calculate the molar mass of this. So 14 times 2, 12.01, plus 1.01 times 18 plus 2 times 14.01 plus 5 times 16, and I get a molar mass of 294.34. Now that actually exactly matches the molar mass of the molecular formula, so as a result we don't have to scale it up because the empirical formula's molar mass is equal to the molecular formula's molar mass, so we don't have to scale up anything, and thus our answer will be, it seems like A will be our answer. Now let's move on to number 9. So number 9 comes from the Chemistry Olympiad, which means it's going to be a little bit hard, but we're going to get through this together because anything is possible when you think hard enough. So, a typical polyethylene bag from a store weighs 12.4 grams. How many molecules of ethylene must be polymerized? Now, they didn't include combined. I included it because you don't know what polymerization is, so I told you what it is. It means to combine stuff to make a bag. So it says, how many C2H4 molecules does it take to make 12.4 grams of a bag? Now, we have to figure out something. So we have to figure out how many molecules of C2H4 weigh 12.4 grams. So there are many ways to go about this, but what I like to do is that I like to find the mass of an individual C2H4 molecule in grams. So we know that 1 mole of C2H4 weighs, I don't know, we have to find the molar mass. So 12.01 times 2 plus 1.01 times 4. Notice how this is from the periodic table, and I'm just grabbing the molar masses from there. So I get a molar mass of 28.06 grams. So in 1 mole, there are 28.06 grams. But I want to know how many grams there are in 1 molecule. But I'm glad that we know what that is, because actually 1 molecule has 6.022 times 10 to the 23rd molecules in it. So let's try to figure this out. So if we want 1 molecule, so let's write 28.06 grams per mole, and let's convert the moles to molecules. So in order to do that, a mole goes on top, a mole of C2H4, and on the bottom we have a molecule of C2H4, but every mole has 6.022 times 10 to the 23rd molecules of C2H4. So what we're doing is we're dividing 28.06 by 6.022 times 10 to the 23rd. And remember to put parentheses around this when you're doing it in your calculator. So I got an answer of, well, let me erase this first. An answer of 4.65, actually 660, times 10 to the negative 23rd grams per molecule of C2H4. So now we have to find how many molecules of C2H4 are needed to make 12.4 grams. So this is where algebra kicks in. So this number times X number of molecules will equal 12.4 grams. So notice how molecules cancel out and you're left with grams. But we need to figure out what X is. So in order to do this, we shall divide this number on both sides. So let's divide 12.4 divided by 4.660 times 10 to the negative 23rd. So I got an answer for X, and it states that X is equal to 2.661 times 10 to the 23rd. And let me keep track of sig figs, because since 12.4 at 3, I have to keep my final answer as 3 sig figs. So it seems like our answer lies around 2.67 times 10 to the 23rd. We're just like, I guess, 0.01 off, and that's fine because this is multiple choice and this is very close, so that's our answer. So let's move on to number 10. Now this is another chemistry Olympiad question, so expect it to be a little bit challenging, but anything is possible, so let's do this. A student is asked to determine the degree of hydration. So the degree of hydration is the amount of water molecules that are attached. So, of a salt by finding the mass of a clean dried crucible and lid, followed by the mass of the crucible and lid containing a sample of the salt. So the crucible, lid, and salt are heated in a Bunsen burner, cooled, and weighed. If the crucible, lid, and salt are heated only once instead of the recommended 3 times, what will be the effect on the degree of hydration compared with the actual value? So now, this sounds a little bit complicated, but let's think about this. So we have a crucible, which kind of looks like a pot, a really tiny pot with like a lid, and then there's some salt in it, and when you heat it, remember, when you heat it, the water will escape because the hydrated form will be converted into the anhydrous, and the water will just, kind of escape from it into the air because it gets evaporated away. So if you heat it 1 time instead of 3 times, then obviously less of the H2O will leave, and not all of the salt will be converted into the, anhydrous form. So let's make a table in order to visualize this. So when we calculate the empirical formula for the salt, we have the salt here, and we have the H2O. So let's do 2 columns. Let's make this the first heating, and let's make this the third heating. So I'm going to use some made-up numbers in order to simulate what the question is talking about, and this is a great way to answer questions that involve experimentation such as this one. So let's just say that we had 30 grams of the salt, and let's say that the molar mass of the salt is 100 grams per mole. So let's say after the first heating we have 20 grams of the salts left and 10 grams of the water escaping. So how do I get this? Well, 30 minus 20 is 10. So let's say that after the third heating, let's say we have only 10 grams of the salt left and 20 grams of the water escaped. So now let's calculate the moles. So 20 grams divided by 100 grams per mole is 0.2 moles, and 10 divided by 100 is 0.1 moles. And on the right hand side, we know that the molar mass of water is 18.02, so 10 divided by 18.02 is 0.555, and 20 divided by 18.02 is 1.11. So notice how I'm ignoring significant figures because in this problem we just need to know A, B, C, or D. So this is not a lab, this is just a simulation. So we don't have to be too serious about this in terms of sig figs. So let's now calculate the empirical formulas for each of the salts based on, the data after the first heating and the third heating. So we would take the smaller of the two, which is 0.2. So we are going to divide both of them by 0.2 and this by 0.2. And we get a 0.555 divided by 0.2 is 2.775. And I'm just going to write that as 3 for simplicity. Now let's do it after the third heating. So after the third heating, we have 0.1 moles as the smaller of the two. So we're going to divide both by 0.1. And in the end, we get 1.11 divided by 0.1. I get about 11. So the degree of hydration after heating it once was calculated to be 3, while the degree of hydration after heating it 3 times gave us 11, and this is because more water escapes when you heat it more, and it shows in, the masses of the water. So this could have been solved by just looking at it, but by doing it like this in terms of doing a simulation, it gives us a better way to visualize what is going on, and it makes sense. So the question asked, if you heat it 1 time instead of 3 times, what is the effect on the degree of hydration compared with the actual value? So let's look at that. The degree of hydration heating it once was calculated theoretically to be 1 to 3, but the actual value, which is the one where you heat it more, which gives you a more accurate value, is 1 to 11. So it seems like our degree of hydration is too low, and that is our answer. So let's move on to the next question. The mass spectrum of a diatomic molecule is shown. So diatomic tells us something. It tells us that maybe this bar is composed of 2 molecules, or 2 atoms, while this shows maybe 1 of the 2 atoms. Just like how we did it for bromine, if you remember from the very first video of this unit. So if this is 1 of the 2 atoms, then this is just 1 atom, so we'll label that atom as X, and this atom apparently has an atomic mass of around, between 13 and 16. So I know you can't see it, but the molar mass, or the average atomic mass of the H, or just one of the 2 H's in H2, is 1.01, and that's not close to 14, so we X that out. Now lithium, we can use a chart for that. Apparently lithium has an average atomic mass of 6.94 on the very left, and let me take that out. So 6.94 is not close to 14, so that's out. Now what about nitrogen? Well, nitrogen is 14.01. So it seems like nitrogen is our answer, and I know there's a C and a DD. That's weird. Let me fix that and make that an A and make that a C. Sorry for the confusion. How about this? I'll make this a B as well. So I'll fix that later, but that's not the point. And let's look at O. Well, O is oxygen. It has an average atomic mass of around 16 AMU. So 16 is not close to 14, so that is not our answer. And notice how 28, which is shown here, is composed of 2 atoms, or X2. In this case, it's N2 gas. And notice how the molar mass, or the average atomic mass for nitrogen gas, which is N2, is 14.01 times 2, which is 28. So the element that best fits this spectrum is, nitrogen, and it's in the form of N2. Let's now move on to the next 3. Sulfate is a polyatomic ion, not a diatomic molecule, not a cation, because sulfate is negatively charged, and it's not a salt. So let's move to our next problem. Sodium sulfate is Na2SO4 because sulfate has a -2 charge and sodium has a +1. So those 2 are out. And it's a strong electrolyte since all salts are strong electrolytes. So our answer is C. Sodium sulfate and calcium acetate solutions are combined and a precipitate of calcium sulfate forms. Write the net ionic equation for this reaction. So let's write sodium sulfate, aqueous, plus calcium acetate. So calcium acetate, this will be 2, and that's aqueous, and they combine to form, well, a precipitate of calcium sulfate. So calcium sulfate, this will be in the solid form, and the final 2 are the ones that we didn't include, which is sodium and acetate. So we have to include sodium acetate, so it would be NaC2H3O2, and this is aqueous. Now let's balance this. So if I put a 2 here, both sides will have 2 sodiums, 2 acetates, 1 calcium, and 1 sulfate. So on the next slide, I will show you the ions separated, and I will show you the net ionic equation. So we see on both sides, the sodiums and the acetates are repeated, which means that they don't react. So they are spectator ions, and I will remove them. So this is the net ionic equation, and note that the net ionic equation for double displacement reactions is the formation of the precipitate. So now let's do number 15. Write the net ionic equation given the reactants for this neutralization reaction. So neutralization reactions involves the transfer of an H+ from the acid to the base. So let's do this. Nitric acid, HNO3 aqueous, plus sodium acetate, NaC2H3O2. Oh, I didn't need to put the parentheses since there's only one of them. So let me remove that, C2H3O2. Now, I think it's easier to do this when we separate them, so let's just separate them right now. So, H plus aqueous plus NO3 minus aqueous plus Na plus aqueous plus C2H3O2 minus aqueous, and that will give you, so we have to transfer the H plus in HNO3 to the base, which is C2H3O2, since this is a neutralization reaction, and we're assuming that the nitric acid is our acid, and the acetate and sodium acetate is our base. So if we do this, we get HC2H3O2 aqueous. This is acetic acid because the H plus gets transferred to the base. And note that I don't transfer it here because why would an H plus want to be with an Na plus? And as you'll see later, Na plus is actually a spectator ion. And then in the end you get Na plus aqueous and NO3 minus aqueous. So to do neutralization reactions, I tend to split my ions and my salts apart. So let's look at the spectator ions. This is a spectator ion. This is a spectator ion because they're on both sides, and now let's remove them. So this is the net ionic equation, and remember that nitric acid is a strong acid, and sodium acetate is not on our list of strong bases like sodium hydroxide, which is a strong base. So this is a weak base. So let's do the next question. The next question will be, which of the following is a synthesis reaction? Synthesis means combining two compounds or substances A and B to form one. So in this, is 2 or 3 or 4 becoming 1? Well, 1 is becoming 2. So this is out since that's decomposition. Now what about this one? 2 becoming 1. That seems right. What about this one? CH4 plus 2O2 becomes CO2 and H2O. This is a combustion reaction, so it's out. And this one is single displacement because we have charges being transferred. So Cl would be gaining electrons, and bromine would be losing electrons. And yeah, it's not D, and B is our answer. Number 17. This one is a hydrate problem once again. So copper 2 sulfate and 5 waters. So copper 2 sulfate pentahydrate is a hydrate. If 30.00 grams of the hydrate is heated so that all the water in the hydrate evaporates, how many grams of copper 2 sulfate will be left? Alright, let's think about this. So we have 30 grams of the hydrate, so CuSO4 and 5H2O. Let me shade in that dot. And this is 30 grams. And then it says it'll heat it all up and remove all the H2Os. So in the end, we will have only copper 2 sulfate. And it says how many grams will be left. So there are many ways to do this, and I will show you one of them. So in order to do this problem, we need to find out how many moles of copper 2 sulfate pentahydrate there are, and that will tell us how many moles of copper 2 sulfate there are, and by converting it back to grams, we will find the mass of the copper 2 sulfate. So as a result, we can write a reaction for this. So copper 2 sulfate and 5H2O. are transformed into just copper 2 sulfate and 5H2O. Notice that in the reaction, this and this is in a 1-to-1 ratio. So I will show you how this applies. So let's convert grams of copper 2 sulfate pentahydrate into moles of copper 2 sulfate pentahydrate. So we have to find the molar mass of copper 2 sulfate pentahydrate. So let's do that. So here's a periodic table, and we need to find the molar mass of copper 2 sulfate pentahydrate. So copper is 63.55. Sulfur is 32.06, and oxygen is 16.00. So let's add that up. 63.55, which is the copper, and we have 1 sulfur, so 1 sulfur is 32.06. So we have 4 oxygens and copper 2 sulfate, so 4 times 16.00. And once you add all this up, we get that copper 2 sulfate alone has 159.61 grams per mole. But we need to remember the 5 water molecules that are attached because it's a pentahydrate. So each water is 18.02, and there are 5 of them, so we have to multiply by 5, and we get, let's see, 18.02 times 5, and then plus 159.61. We get 249.71 as our molar mass for the copper 2 sulfate pentahydrate. So let's divide 30 by the molar mass, which is 249.71. So we get that we have 30 divided by 249.71, and that will be 0.1201 moles of copper 2 sulfate pentahydrate. Now we know that the ratio between copper 2 sulfate pentahydrate and copper 2 sulfate is 1-to-1. So we can do the math, and we can say that, well, 0.1201 moles of copper 2 sulfate pentahydrate. So I'll write that as the hydrated form, and I'll multiply by the conversion factor. The hydrated form and the anhydrous form is in a 1-to-1 ratio. So 1 mole of H over 1 mole of anhydrous, and we get in the end 0.1201 moles of the anhydrous copper 2 sulfate. So now we need to convert the moles of copper 2 sulfate anhydrous into grams. So I just have to multiply by the molar mass of copper 2 sulfate alone, which is 159.61. So 159.61. And we wind up getting 19.18 grams. So that is our answer. The answer is A. Now let's do number 18. 6 moles of C2H4 undergo combustion with 6 moles of O2 in a sealed container. What is the limiting reactant, and how many moles of substance are there following the reaction? So our reaction, we will assume, goes to completion because it is combustion. So C2H4 plus O2 becomes CO2 plus H2O. Now we have to balance this, so I would put a 2 here, and let's count the carbons. So 2 carbons, so let me write it like this: 2 carbons, 4 hydrogens, and 2 oxygens. And on the right hand side we have 2 carbons, it seems like there are 5 oxygens, and there are 2 hydrogens. So now we have to balance this out. So I want to balance the oxygens next, so let me put a 2 there. And if I put a 2 there, then we will have 6 oxygens in total and 4 hydrogens in total. Now we have to balance the oxygens now, so I'll just put a 3, and that will become 6, and our reaction is balanced. So let's see, what is our limiting reactant? Well, we have to find whichever one produces less product. So 6 moles of C2H4 will produce 12 moles of CO2, which will be the product that we will focus on, since for every one C2H4 we have 2 CO2s, so it's twice as many moles. Now what about O2? Well, if it's a 3 to 2 and we have 6 moles of O2, then we will produce 4 moles of CO2 based on proportions. So this is 4 moles of CO2. Now the one that produces less product is going to be our O2. So that is our limiting reactant, and let me fix the 2. And thus C and D are out, so our limiting reactant will be O2, so it's either A or B. Now let's find the total moles of substance in the container. So I wrote a before and after chart. So before we had 6 moles of C2H4 and 6 moles of O2 and nothing else of CO2 or H2O. Now after the reaction, we know that since O2 is our limiting reactant, we can produce at most 4 moles of CO2. Now if we produce 4 moles of CO2, how many moles of H2O will we produce? Well, according to this reaction, the ratio at which CO2 and H2O are formed are 2 to 2, or 1 to 1. So therefore, if we produce 2 moles of CO2, we will produce 2 moles of H2O. And therefore, if we produce 4 moles of CO2, we will produce an equal amount of H2O, or 4 moles of H2O. So now let's figure out how much stuff gets consumed. Well, we know that 6 moles of O2 are consumed completely since it is the limiting reactant. So all the O2 moles will be consumed first, so we will have 0 moles of O2 in the end. Now, how many moles of C2H4 do we have left? Well, if we had 6 originally, let's figure out how much gets consumed. If 6 moles of O2 are consumed, how many moles of C2H4 are consumed? Well, they're in a 1 to 3 ratio. So as a result, if we consume 6 moles of O2, we will consume 2 moles of C2H4. And I found that just by multiplying and scaling up the reaction by 2. So if we consume 2 moles of C2H4 and we had 6 originally, then we would have 4 moles of C2H4 left over, because 6 minus 2 is 4. Now, adding all of this up, we will get 4 plus 4 plus 4 is 12, so our answer will be B. So let's now look at our next question. Let me clear the ink and let me circle B. Mercury 1 nitride is, well, this is a salt, and mercury 1 nitride, well, remember, mercury 1 is Hg2 2 plus, because each of the mercuries have a plus 1, so 2 mercuries will have plus 2. So that's a neat way to remember it. And nitride, since it ends with an IDE, will be N3 minus. Nothing special there. So in order to combine these, we will have to have 3 of these and 2 of these. And a nice way to remember it is by taking the charge of the first and making it the coefficient of that, and making the charge of the second the coefficient of the first. So this salt will be Hg2, and there are 3 of them, and N2 because there are 2 and 3 minuses. So this will actually be C, and that is our answer. So the last problem asks is, how many neutrons are in tungsten 184? We have to find the number of protons, which is the atomic number, and the atomic number for tungsten is 74. So 74. And to find the number of neutrons, we subtract the mass number by the number of protons, and we get 110 neutrons, and that is B. So this is the multiple choice section, and the next section will encompass the free response questions, which will not have multiple choice. So I hope you learned a lot, and have a nice day.